Here's a quick review of what we were doing last time. So we started our discussions on transformation of pairs of random variables, so functions which involve pairs of random variables. And like I said, there are going to be two cases. The first case is a simpler one, and this is the only case actually we're going to be doing, which is z equals g of xy, right? So this is the case we're discussing, where the two random variables x and y, they have some joint PDF, and from that joint PDF, so they have just joint PDF, and their input to a function, which is a two-dimensional function. So it takes in two inputs, and the output is z. And the question that we are trying to address is, okay, given the joint PDF of x and y, we're required to determine the PDF on z, right? And I mean, there's no fixed formula per se. I mean, it's just the approach that I outlined was that we're going to compute the PDF, CDF first, involving integration over a two-dimensional region, and then differentiating that CDF with respect to z, and then obtain the PDF for z in the process. So this is two steps, right? So this is step number one, and then step number two. Okay. Then we started talking about some examples. The first example was if x and y are jointly distributed, and z is a sum of x and y, right? And we did some analysis, some derivations, and this is the conclusion we had. Okay, the PDF on z turns out to be given by this relationship, and if x and y were independent of each other, then it turns out that if the PDF of z is just a convolution of the PDF of x and the PDF of y, right? So that's an important result, which is kg if x and y are independent, the PDF of z equals xy is equal to the convolution of the individual PDFs of x and y. Okay. Then the second example we were doing was this, where x and y were Gaussian, and they were independent of each other, and they were identically distributed as well. So when I say they are identically distributed, that means they have the same PDF, they have the same mean, and they have the same variance. Does not mean that they're the same random variables. They follow the same distribution, but they are different random variables, and they are independent of each other. Okay. So x and y are Gaussian, as zero mean Gaussian with variance sigma squared. And we were interested in finding the PDF of z equals x squared plus y squared, right? So this is what we were interested in finding, z equals x squared plus y squared. Okay. And it turns out, okay, you do the analysis, and we found out that the PDF of z actually turns out to be an exponential distribution, right? So this is the exponential distribution that we found. Okay. All right. So and the way we went about this was through conversion to polar coordinates. Okay. I'm going to continue with some examples before we end this chapter. The next example I have is very much related, which is example 3. So once again, x is Gaussian. All right. Okay, so x is Gaussian with zero mean and variance sigma squared. Y is Gaussian as well with zero mean and variance sigma squared, and rho xy equals 0. And that means they are not correlated with each other. Okay. And that means they're independent as well. So remember, Gaussian random variables, if they're uncorrelated, they're guaranteed to be statistically independent as well. And the z is root x squared plus y squared, right? So it's pretty much the same as the previous example, except that I have a root here, right? So if x and y were the x coordinate and y coordinate of a body, the previous example that we did was finding the PDF of the squared distance from the origin. And this is actually the distance from the origin, right? So if x and y were the coordinates, with the x and y coordinates of where the body is located, and if x coordinate and y coordinate is Gaussian distributed to both of them, We're interested in finding what PDF or what distribution does the distance from the origin follow. Okay, this is what we're interested in finding. And it turns out the answer is, or the way I'm going to go about this is exactly the same. Fz of z is equal to the probability that capital Z is less than or equal to small z, which is probability that root x squared plus y squared is less than or equal to small z. And this is just equal to the probability that x squared plus y squared is less than or equal to z squared, right? They're the equivalent events, okay? Because they're equivalent events. And from here, it turns out k f z of z, I'm skipping steps here. It turns out this was exactly the same calculation we did here as well, okay? So this is exactly the same calculation we were doing here in this particular equation, right? Except that in that equation we had x squared plus y squared is less than or equal to z, and this is what we got as the answer, okay? Now the only difference here is that we're interested in finding the probability that x squared plus y squared is less than or equal to z squared. All I'm going to do is therefore is just replace z with z squared, right? And I'm going to get the CDF, and the CDF turns out to be 1 minus, okay, 1 minus e raised to power minus z squared by 2 sigma squared and times u of z. And the reason is because the radius is always positive, right? Or the radius is always non-negative. Okay, so this is the CDF for this particular z. And how do I find the PDF? The PDF is just obtained by differentiating the CDF with respect to z. And what I get here is z upon sigma squared e raised to power minus z squared divided by 2 sigma squared u of z. So this is what I get after I differentiate. What kind of a PDF is this? What kind of a random variable is this? Anybody? So what kind of a random variable would z be? I mean, we said the distance squared is exponential random variable, right? That's what we said.
The Rayleigh random variable.
So this is a Rayleigh random variable, good, right? So this is Rayleigh. Right? So it turns out, okay, if x and y are independently Gaussian distributed, identically distributed, and zero mean, the x squared plus y squared root, or the distance from the origin, actually follows a Rayleigh distribution. So that's a result that we've been able to derive. Okay. So let me do an example 4 here, and which once again is related to the same set of x and y. So once again, x is Gaussian, zero mean, variance sigma squared. Y is also Gaussian. Y is also Gaussian, zero mean, sigma squared, and rho xy equals 0. But what the z is, see, x and y coordinates हैं, ठीक है? Is distance from the origin, क्या चीज रहेगी? Distance के अलावा. So if you, in the polar coordinates, something else you have is the angle or the theta. ठीक है? So let's say z equals tan inverse y by x, right? Which is in fact the angle. Okay. So if x and y were the coordinates of a body in a two-dimensional coordinate system, and we found out that the PDF or the distribution of the distance from the origin follows a Rayleigh distribution, and now we're interested in finding here, what about the angle? What about the angle z that it makes with the positive x-axis, right? what distribution does it follow? That's the question that we're interested in answering. Okay. So how do I go about this? I once again follow exactly the same methodology. I am going to find out what the PDF is. So this is the probability that capital Z is less than or equal to small z, right? And this is the probability that tangent inverse y by x is less than or equal to small z. And how do I do this? So in order for me to do this, I just need to integrate the joint PDF. The joint PDF is 1 upon 2 pi sigma squared e raised to power minus x squared plus y squared by 2 sigma squared dx dy. Why is this the joint PDF? Kyun Isha? Why is this the joint PDF?
सर एक्स स्क्वायर जो हमने इनिशियली जो प्रॉब्लम एट हैंड लिया उसके लिए हमने यही किया था इवैल्यूएट पिछली क्लास में.
I mean, why is this the PDF? I mean, why not something else?
Because हमने कहा है कि वो नॉर्मली डिस्ट्रीब्यूटेड हैं and the exponents they will add to give us this.
Why? Correlation किधर गई?
Uncorrelated हैं तो
good.
independent हैं.
They're independent. Good. And
So
therefore,
which is why okay, exactly वो product होगा.
exactly. So therefore, the marginal PDFs are the product of the marginal PDFs gives you the joint PDF. So all I've actually done is I have multiplied two Gaussian PDFs together, right? The PDF of X and the PDF of Y, right? And this is the joint PDF therefore that I get. Okay. Now, what should I integrate this over? Abdullah, what should I integrate this? I mean, what region should I integrate this over with? यहाँ पे क्या होना चाहिए? I mean, this is orange blob that you see.
Seeing. Just a minute. So the region where x and y are defined.
So how should I exactly? So the region where x and y should satisfy some property, right? So what property do they satisfy? Should they satisfy in that region?
Sir, where tan inverse is defined for y over x.
Okay, so tan inverse of y by x is always defined. So basically, this is the region that you're trying to integrate over, right? So if this is the x and y plane, right, and this angle is z, so the integration is actually here. This is what you're integrating over, right? Because this, in all of these points that reside on this region, I know that tan inverse y by x is actually less than or equal to z. And of course, when I say less than, so I'm assuming that the angle is always between 0 and z. Okay, so 0 and 2 pi के दरमियान में angles को मैं consider कर रहा हूँ. Okay, so this is 0 is less than equal to tan inverse y by x is less than equal to z. Okay. The more important question is, how do I evaluate this integral? So how do I evaluate this integral? Q Salman, what do you think?
Sir, जो बाहर वाला इंटीग्रल है वो तो माइनस इन्फिनिटी टू इन्फिनिटी है.
Okay.
और जो इसकी जो दूसरा वाला जो x वाला है ना,
Yeah.
इसका जो इसकी जो अपर लिमिट होगी हमारे पास, लाइक लोअर लिमिट तो माइनस इन्फिनिटी होगी. अपर लिमिट जो है वो x in terms of z and y.
Okay. Yeah, so that Salman, that's one way to do it. लेकिन जो है that will be there's an easier way of doing it, because of the fact that यहाँ पे ये है x squared plus y squared है, right? उसकी वजह से एक चीज आसान हो जाएगी किसी एक तरीके से।
सर क्या हो जाएगी?
आसान कुछ हो जाएगी, कोई एक आसान तरीका है, मच ईजियर सॉल्यूशन। ईशा?
सर दोबारा पोलर कोऑर्डिनेट्स में जाके थीटा पर हम कंडीशन z की लगा दें अगर।
So the easier way, Salman, is to use polar coordinates, because I see that x squared plus y squared is the radius. It's going to come very easy, and I just want the theta should be less, or the angle should be less than something, right? So that means I should really be going to the polar coordinates, right? So if I go to the polar coordinates system, that means I have, this is 1 upon 2 pi sigma squared. This is e raised to power minus r squared by 2 sigma squared. This is, so I'm going to pull out r here. This is dr, d theta, and this is r here, right? So dx dy is r times dr times d theta. Okay. As far as the radius is concerned, radius actually goes where? Radius goes to 0 to infinity, and theta goes from where to where? 0 to z. Okay, so that's an integral I need to solve now, right? This is not too hard. This is 0 to z, right? And then I observe kr, this r divided by sigma squared. This r by sigma squared, once again, is the derivative of this thing here, right? And that makes my life easy, right? So this becomes e raised to power minus r squared by 2 sigma squared. I need to have a 1 upon 2 pi here, and this goes from 0 infinity here and d theta. And the reason why I flipped the limits is because of the minus sign. Okay, so that's a small step I've missed. It turns out that this is just 1, right? So this is 0 to 2 pi, 0 to z, and this is 1 upon 2 pi times d theta, because the other thing is just equal to 1, and therefore this is z upon 2 pi, as long as 0 is less than equal to z is less than equal to 2 pi. Okay. Now, if you differentiate, what kind of a random variable will this turn out to be? So what would be fz of z? I just differentiate, right? G Mosen?
नहीं सर ठीक है।
Question था या you want to answer?
Sir, I wanted to answer, लेकिन I'm withdrawing for
Okay. Okay.
Sir, may I guess?
हाँ जी, बताएं। वो answer is already there in the chat box वैसे, but
Uniform.
Yeah, it's a uniform random variable. So if I just differentiate, this is what I get, right? So this is 0 is less than equal to 0 equal to 2 pi, and is 0 otherwise. Okay, so this is my answer. So that means is K, which is an interesting result, which says K, the angle that the body makes with the positive x-axis is going to be uniformly distributed between 0 and 2 pi. The radius is going to be Rayleigh distributed, and the angle is going to be uniformly distributed. Okay. Now, mind you, this is only for the case when x and y are independent, they are Gaussian, and they're zero mean, and they have the same variance as sigma squared. Now, if I change any one of these conditions, things might change, and they should change, right? So theta may not, for example, be uniform, right? Or z may not, the angle may not be uniform if, for example, x is sigma squared and y is 2 sigma squared, right? So then x may not be uniform, and things, and I'll leave you to try those variations on your own. Okay. Now, so this is almost the end of our discussions on transformation of pairs. All I want to say about case 2, which is actually important, but we're going to skip this, and is there in the textbook, which is K. So case 2 is of the following form, that if z equals some function, is some function of x and y, and w is another function of x and y. Okay, and the textbook deals with this case differently, as it should, right? So this case needs to be dealt differently than what we've done already. Okay, now the question I have for you is why, right? Because I mean, why does it need to be dealt with differently? I mean, can't you just say, okay, what I'm going to do is I am going to apply whatever I did up above, which is case 1, on z, on the function g, and I'm going to do this again for this f of xy as well, right? And if I apply the case 1 on the first function, and then I apply case 1 on the second function, that will yield for me the PDF on z, and that will yield for me on the PDF of y as PDF of w. Okay, and we're done. Why do we need to do this separately? Any thoughts on that?
Sir, question please repeat. I didn't get the question.
हाँ, question ये है कि you see case 1 क्या था? Case 1 था कि जी, if I give you z equals g of x, y, given the PDF of x and the PDF of y, I can determine the PDF on z, right? That's case 1, right? Now, if I know case 1, I can apply this case 1 to z, and I apply this case 1 to w as well. इसको भी apply कर दूं, इसको भी कर दूं, मेरे पास PDF z की भी आ जाएगी, and I'll also get the PDF of w, both of them. ठीक है? So then, I mean, why do we need to do this separately? So Mohsen, I'm going to come back to you before I talk to Shoaib. Yes, Shoaib.
सर लेकिन ये तो जब भी पॉसिबल होगा ना जब x और y दोनों इंडिपेंडेंट हैं.
Not necessarily. क्यों?
So अगर हमारे if x and y were independent, then जो हमारे पास, then we could have done this, मतलब case 1 on both. लेकिन अगर हमारे पास independent नहीं है, तो we cannot follow the procedure above, isn't it?
No, why not? I mean, all of that procedure above was not applicable to independent random variables. I mean, if I led you to believe that, that's incorrect. Right? So all of this procedure above, no, even though the examples, that the last 3 examples we did was for independent random variables, but what about the convolution here? ये जो white में result है, ये वाला, this does not apply to independent random variables. This is applicable to dependent random variables as well. So the results, all of that results above in general, apply to random variables which could either be dependent or independent. Okay, Shoaib? So the answer is something else. G. Mohsen, do you want to say something?
Sir, along similar lines मैंने argument देना था कि हम पीछे consider कर रहे थे कि x और y jointly Gaussian है, right? तो उसकी कुछ guarantees थी जिसकी वजह से कुछ simplifications हो जाती थी, लेकिन we won't have the same guarantees for z and y.
Okay, so let me reiterate. Let me reiterate once again. The case 1 that we did, the procedure that I outlined is not just applicable to independent Gaussian random variables. Like, those were just examples, right? And that's one of the common mistakes that we do. कि हम एक example देखते हैं, and then we start generalizing it कि यार अच्छा ये this is the only scenario in which this is applicable. And that's why I told you थोड़ी देर पहले भी, you start applying this to variations. Rho को आप, and I may give you this as a homework problem, okay, x and y are not independent anymore, okay, and you will still be able to do everything that I did earlier. You'll get different results, but the procedure is still applicable. Okay, Ji Isha, you have a question?
Sir, I just wanted to take a guess at why we're going for case 2.
Yeah.
And that maybe because that z is also dependent on x and y, and w is also dependent on x and y.
Yeah.
So perhaps they both are related to each other.
What? So you're at the right track. Cons who are related to each other?
Z and W.
Z and W, right? So that's actually the answer, because if I apply the case 1 to Z equals G of XY separately, and then apply case 1 to W equals F of XY separately, all I'm going to get is the marginal PDF of Z and the marginal PDF of W, right? What I won't get is how Z and W are jointly distributed. Right? That's what I won't get, right? So in order for me to determine or evaluate the joint PDF of Z and W, that's why this case needs to be dealt with separately, okay? Because it may, if X and Y are independent, okay, Z and W are not guaranteed to be independent, right? So let's let that sink in for a while, right? So if X and Y are independent, there is no guarantee that Z and W are going to be independent as well. Okay? Can somebody give me a counterexample? Disha?
Sir, if Z is equal to X plus Y and W is equal to X square plus Y square?
Yeah, okay. But the easiest one I was looking for is if Z equals X plus Y and W equals 2 times X plus Y. Right? That means even though X and Y are independent, Z and W are not going to be independent. In fact, Z and W are deterministic functions of each other. I mean, one is just twice the other. Okay? So those are directions that we don't have time to go into. I am not going to discuss this anymore. So there's a derivation behind this. जिसके पीछे Jacobian इस्तेमाल होता है, and I will skip this year. Okay. But that's there in the textbook. For those of you who are interested, they are more than welcome to go ahead and read. It's not that difficult. Okay. So so this is skipped. But encouraged to take a look on your own. All right. Okay. Any questions here before I move on? Okay, no questions. So this is where I am going to start this new chapter. So this is chapter 6. So I'm just sort of combining chapter 6 and chapter 7 into a single section, picking some stuff from here and picking from stuff from there. So chapter 6. Okay, so this is basics. So this is multiple random variables. So now remember the logic that we've been following, especially with the logic that, or the flow that this textbook follows, which is talks about single random variables first, transformations of single random variables, and then generalizes it just slightly and talks about pairs of random variables and transformation of pairs of random variables. Okay. So from 1 to 2. Now the next logical step is to go from 2 to many, right? So many more, right? So those are just generalization of all of the concepts that we've discussed before. And that's why I am not going to spend a lot of time on describing what these joint PMFs are and so on and so forth. Okay, I'm just going to list them for your reference. All right. So remember, these are the chapter title or is multiple random variables. Okay, so more than 2 random variables, right? And the first thing I'm going to talk about is joint PMFs, CDFs, or PDFs, right? These are just generalization of ideas that we've done already. Okay, just trying something out. All right. So for n random variables, where this capital N could be 2 or more, right? Or actually 1 as well. For n random variables, x1, x2, dot, 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 xn, we have the joint PMF described over all of these random variables, x1, x2, dot, 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 to xn, evaluated at small x1, small x2, dot, 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 all the way up to small x sub n, is defined as the probability that capital X1 equals small x1, capital X2 equals small x2, and all the way up to Windows. So all the way up to capital X sub n equals small x sub n, right? Similarly, I can define the joint CDF. This is x1 all the way up to x sub n. This is just defined as the probability that x1 is less than equal to small x1, x2 is less than equal to small x2, all the way up to x sub n being less than equal to small sub x sub n. Okay? The joint PDF. So what will this be? So Josefa, what do you think this will be?
So the derivative of fx1 to xn.
Right. So partial derivative with respect to x1 all the way up to x sub n of what? Of the PDF. x1 all the way up to x capital N. Okay? Now, as you can see, this becomes quite cumbersome to write. I mean, all of these things together, right? So that's why we typically use vector notations, right? And that's why when we're talking about multiple random variables, we often refer to them as random vectors, because random vectors are nothing but a collection of multiple random variables put together, right? As a collection, right? So vector notations, we're going to keep on using from here on. And we're going to say that capital X bar represents a random vector, which is equal to the collection of x1, x2, all the way up to all of those n random variables put together into a vector. That's a random vector x bar. Okay? And by default, all of the vectors that we're going to consider from here on are going to be column vectors. Okay? By default, vectors that we're going to consider are going to be column vectors. Now, at the same time, I can define a vector small x as well, which is just a collection of those small x1, x2, all the way up to xn in a column vector format, right? Now, given this notation, we can use a notation for example, f of the random vector capital X bar evaluated at small x bar, right? So this is just a shorthand notation for this thing. So for this 3. So this is 3. Right? Similarly, I can have a p x bar small x bar, right? So this is 1. And similarly, पहले मुझे वो करना चाहिए था, लेकिन right, and f x bar evaluated a small x bar, so this is 2. Okay, any questions here? So simple enough. So this is just a vector notation that we're going to use, all right? Now, what about conditioning? I mean, from before this, the conditional PDFs that we talked about were only for pairs of random variables. We said, what is a conditional PDF of x1 given an observation on x2 or vice versa? Or given a, so what is the PDF of x given an observation of y, right? Or vice versa, right? So we're only talking about two random variables, but we can extend that idea to multiple random variables very, very easily, right? So I can say, okay, what is the condition PDF of capital X1 all the way up to X capital M given observations on all of these random variables from xm plus 1 all the way up to x sub n. Okay? Now this is evaluated where from x1 all the way up to xm given the observation small xm plus 1 all the way up to xn. Right? And it's pretty straightforward. What would this be equal to? This will be equal to the joint PDF of everything put together, x1 to x capital N, divided by what? Bilal, can you hear me? Right, so who's going to answer this? I mean, divided by what? What should this be divided by? Salar, Ali, Huzaifa?
Probability होती थी.
Probability? What should this be divided by? Okay, this cannot be divided by the probability. These are continuous random variables. The probability is 0. Shoaib?
सर वो जो given that के बाद है, so PDF of x of m plus 1 dot 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 x of m.
Good. Right. So the PDF of xm plus 1 dot 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 to xn evaluated as small x m plus 1 all the way up to small x. Okay. So it's a joint PDF, right? So these are just basic ideas which I'm going through quickly. What about independence? So we say that the n random variables x1 through x sub n are independent if and only if the joint PDF of the vector turns out to be equal to the product of all of the marginals. Fxi, small xi, right? So this is when the n random variables are independent, statistically independent. Okay? Achha. So we're going to continue with the basics. Expectations. Involving multiple random variables. Now, here's some notation that we're going to use. No, okay. So here's a notation we're going to use. So I am going to define the expected value of a random vector. What do you think that the definition? I mean, have you come across this before? So what is this equal to? Right. So this is something which we've not come across before, but I just want to emphasize the notations that we're going to keep on using from here on. So we say, what is the expectation of a random vector? What I mean by that is that this is actually equal to expected value of x1, expected value of x2, all the way up to expected value of come on. Okay, so this is expected value x2 all the way up to expected value of xn whole transpose, right? So essentially what I'm saying is that the expectation of a random vector is defined as the expectation actually going inside the vector and applying expectation to each and every individual components of that vector separately and independently. Okay? So if I have a random vector x1 through xn and I say, okay, what is the expectation for this random vector? What I mean by that is this is going to result in another vector which is going to contain the expected values of each and every one of those individual random variables put together. Okay, that's what this notation is going to mean. Okay, and this is really equal to mu1, mu2 all the way up to mu n whole transpose, right? And we say, yeah, this is actually the mu vector, right? So this is what I mean by the mu vector. The mu vector is the expectation of the random vector. Okay. Any questions here? Because I'm going to now start building up on this notation quite a bit. Okay, about this notation. Any questions about this notation? So it's important that you get this clear. Okay, so the expectation of a vector, basically what this means is the expectation goes inside the vector, right? And it applies individually to each and every one of the elements of the vector. Okay, and by extension, we also say this expectation, we're going to extend this inside a matrix as well in a similar fashion. Okay, so here's an important thing we're going to define, which is called the correlation matrix. So who knows, who has come across correlation matrices before? Any ideas what correlation matrix is of a collection of random variables? कहीं ना कहीं पढ़ा होगा शायद, hopefully. क्यों माज? Mohsin, please go ahead.
So guess है diagonals पर आपकी correlation of each random variable होगा और non-diagonal entries पर 0 होगा.
Okay, so that's a guess which is not completely wrong and neither is it completely right. Okay, that's all somewhere in the middle. So what you mean by the diagonal is sort of okay, but the off diagonal elements tell you something else, and I'm going to tell you in just a bit. Ji Isha, you have a comment?
Sir, auto correlation और cross correlation values होंगी.
Okay, so auto correlation क्या होता है? अब आप कहीं और जा रही हैं वैसे.
यानी auto correlation यानी कि within the same with the same random variable and cross correlation यानी किसी और के साथ diagonals and
you're probably recalling some of the things that you perhaps did in comm systems.
Yes.
And those were processes. Okay. We've not talked about processes yet. We're going to build on top of this to describe the process. Okay. So it's important that that we get this right and the concepts right. और process पे आराम से हो जाएंगे सब कुछ. ठीक है. So correlation matrix is defined as follows. So typically we use the notation R to denote the correlation matrix corresponding to the vector X, and is defined as being the expected value of the random vector X times the random vector X transpose. And this is actually, this reminds me of something that Shoaib, I think, mentioned in one of the other classes. So उसने कहा था कि यार दूसरा transpose होना चाहिए. Right? That means he's come across this somewhere. Shoaib, do you recall that?
Yes.
I'm assuming that you had something like this in mind, the correlation matrices.
Yes.
Okay.
Yes.
Right. So why is this a matrix, by the way? So remember, X is a column vector. X is a column vector. You're multiplying that with a row vector, right? So that means X times X transpose is going to be of how much dimensions? It's going to be of n cross n dimensions, right? So this is going to be expected value of, and whatever I have inside the expectation is going to be an n cross n matrix, which has x1 squared here, x1 times x2 here, x1 times xn here, and then this is x2 times x1, this is x2 squared all the way up to x2 times xn, and this is going to be xn times x1, this is xn times x2 all the way up to the end, which is xn squared. So these are the elements inside the product of X with X transpose. And then, when you do the matrix multiplication, this is exactly what you're going to get, right? Now, these white things that you see here, they're actually random variables, and the expectation operation is applied on the outside. And like I said, the expectation operation, we're going to say by definition or notation, we can take it, it's linear, it's going to can go inside the matrices. Okay? So this turns out to be equal to the expectation. Okay, hold on. So this can, मुझे बहुत ज़्यादा चीज़ें लिखनी पड़ेंगी, इसलिए I'm going to skip that. And okay, this can go inside such that R x x I j, what does this turn out to be equal to? RXS ij का मतलब क्या है मेरा मतलब ये है कि यार this is the element of the matrix Rxx at row I and column j. So what do you think is this going to be equal to? I mean, when you do that matrix multiplication. So this is a matrix that I get, right? So this is a matrix that I get, ठीक है, जो कि ये फॉर्म आ गई है, right? इसकी आयत रो पे और जेथ कॉलम पे क्या चीज पड़ी होगी जी मोहसिन?
Sir, expectation of xi and xj.
Good. Expectation of Mohsin, just to clarify, and से मुराद आपकी, I'm assuming product है, right?
Yes, sir.
The expectation of xi times xj, right? So this is the element residing at the ith row and jth column of the correlation matrix. So this is important. So correlation matrix asal mein is a collection of these correlations between pairwise random variables. It's a pairwise correlation between each and every element inside the random vector x. Okay? That's what a correlation matrix tells you, right? So correlation matrix tells you कि यार एक x1 से लेके for example x3, x1, x2, x3 एक random vector था. The correlation matrix tells you okay, what is the correlation of x1 with itself? What is the correlation of x1 with x2? What is the correlation of x1 with x3? What is the correlation of x2 with x1, x2 squared, x2 and x3, and so on. Each and every one of the pair that exists, it tells you the correlation of that pairwise combinations. Okay, that's what a correlation matrix tells you. Okay, any questions? So by extension, what do you think the covariance matrix is going to tell you? Or what is the definition? What will the definition of a covariance matrix be? Jishoy, go ahead.
covariance of x. So basically covariance, and then the whole big bracket, and then we left x1, 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 x2, and so on.
Okay.
Matrix same रहेगा, just covariance capital E की जगह covariance if we can write.
Good. Like in terms of that's exactly fine. That's exactly what it is going to be. लेकिन अगर उसको मुझे थोड़ा सा matrix notations में थोड़ा सा बताइए, Mohsin, if I can come to you.
सर ये RXXIJ minus आपका expectation of XI multiplied by expectation of XJ.
Okay. Right. So not exactly what I was looking. So आप थोड़ा आगे जा रहे हैं. मुआज ने भी हाथ खड़ा किया था.
सर ये वो होगा ना, expected value of vector x minus mu times x minus mu transpose.
Good. Huzaifa, is that what you were about to say or something else?
Yes, sir. Same thing.
Good. Excellent. Right. So this is x minus mu x times x minus mu x transpose. This is what the covariance matrix is. Okay. So all this does is कि x vector लेता है, उसमें से mean vector subtract कर देता है. Remember, I mean, all of these are linear operators. So असल में this is element by element subtraction, and then you do that multiplication of vectors. Okay. And it turns out it's going to be very, very easy to show that Cx, and this is, I think, what Mohsin was referring to. Give me a minute. All right. So I think what Mohsin was referring to was what would Cxx and Ij be? So I think he was saying that this is going to be equal to expected value of xi minus mu I times xj minus mu j, right? So it's actually the covariance between the random variable xi and the random variable xj. Okay? So the element at the ith row and the jth column of the covariance matrix is equal to the covariance between the random variables xi and xj, right? As opposed to the correlation matrix, जहाँ पे the ith row and the jth column element is actually the correlation between xi and xj. Okay, so that's a slight bit of a difference. Okay. Mohsin, is that what you were saying? I believe that's what you were saying when you gave the answer.
Sir, इसके आगे मज़ीद simplification थी.
Okay, so you were saying that this is equal to RXXIJ minus mu I times mu j. This is something you can do as well. Okay, so असल में बात सारी की सारी ये है कि instead of doing each and every one of these operations on each and every one of the element-wise elements of the random vector, we just use vector notation to ease our notation, or vector notation to make it less tedious. I mean, to make it, we don't have to write everything out. I just say a vector x, and I just say x transpose vector mu x, and let's do all of this things. Ek line mein, I just define the entire matrix. Okay? That makes my life a lot more easier. All right. All right. Now here's a theorem here for you, which we're gonna quickly prove. And the theorem statement says that correlation matrices and covariance matrices they are symmetric and positive definite. All right. Now, so who's going to tell me what symmetric matrices are? फिर symmetric matrices क्या होते हैं? जी मोहसिन.
So जिनकी transposition is equal to themselves.
Good. Right? और उसका मतलब असल में क्या होता है कि right, in order to show symmetry, when I say that the transpose of a matrix is equal to itself, what does that mean in terms of the elements?
Elements are a reflection of each other along the diagonal.
So I want to be more specific, somebody to be more specific than that. Ji Mohsen?
Sir, गलती से hand raise हुआ था.
Oh, okay. So, right. So symmetry, a matrix is, so matrix setting R is symmetric if R equals R transpose, right? So that's what symmetry means, right? And which means, and if and only if, that R of ij, that means the element at the ith row and the jth column of that matrix must be equal to what?
R of ji.
R of ji. So that's what Isha meant. So that's what I said, thoda sa aur symmetric, specific, right? And this needs to be satisfied for all I and for all ij, all I and all j. Okay? If a matrix satisfies this condition, then the matrix is symmetric. And if the matrix is symmetric, this condition must be satisfied, right? So that's why there's an if and only if, right? And it's quite very, very clear that the covariance matrix and the correlation matrix are symmetric indeed, right? So it's clear that R, X, X, I, okay, Microsoft is hung up. Okay. So it should be clear that RxX I j is equal to the definition is this is the expected value of xi times xj. But since multiplication is commutative, I know that this is expected value of xj times xi. I mean, both are equivalent. But by definition, this is Rx x ji, which completes the proof. And you can do exactly the similar thing for the covariance matrix as well. I'm not going to do that, right? Now the positive definite thing is more interesting, right? What are positive definite matrices? So what are positive definite matrices? Somebody other than Mohsen, please. Salar, what are positive definite matrices?
I don't really know exactly, but just taking a guess. Maybe it has to do with the diagonals being non-zero.
Okay, not exactly. Diagonals being non-zero is just one class. Like in the definition is more general. G Mohsen, if you want to give it a shot.
Consequence था इसका कि eigen values जो है वो greater than 0 होती हैं.
Okay, good. So that's actually Mohsen a consequence of this. So exactly what I would have said exactly the same thing. A consequence of that is the eigenvalues are positive, but the definition is something else. जिसकी वजह से consequence होता है. Shoaib has exactly the right answer. Ali, you raised your hand as well.
Yes, sir, यही आंसर था मेरे पे.
कौन सा वाला जो चैट में लिखा है?
X जैसे अगर कोई X matrix है तो X transpose EX is greater than 0 होता है इसमें.
Yeah, good. Right. So a matrix R is positive positive definite if and only if this number Z transpose times A times Z, which turns out to be a scalar. Remember, A is an n cross n matrix. So this applies to symmetric matrices, right? So A is an n cross n matrix. So multiplying with Z transpose, you're going to get a row vector. Okay? Z is a column vector. So वो row बन गया, matrix से multiply किया, it becomes a row vector, and you multiply it by Z, and you're going to get a scalar, right? this scalar must be greater than 0 for any z that you choose, which is not equal to 0. Any z in the universe that you can choose, which is not a 0 vector, because this must be equal to 0 for the 0 vector. So apart from that, any other non-zero z that you choose, and you compute this product for that any z, it turns out it will always be greater than 0 if the matrix is positive definite, right? Right? And if this condition is satisfied, this must be positive definite, right? So this is an if and only if, okay? Now we can use the same definition to prove that this condition here must be satisfied for the correlation matrix as well, okay? So we can show that Z transpose times Rxx times Z is greater than 0 for all Z is not equal to 0. That's something we can show. Here's how. So let's do this. Z transpose times Rxx times Z. What is this equal to? This is Z transpose times expected value of X times X transpose times Z, right? What I can do now is, because expectation is linear, I can take the product inside the expectation. I mean, if I can bring it out, I can take it inside as well. I mean, it doesn't really make a difference, right? So this is Z transpose times X times X transpose times Z. Right? This is what I get. Can I say something about what is inside this expectation now? Or can I say something about this? And can I say something about this separately? जी मोहसिन?
सर एक दूसरी टर्म की ट्रांसपोजिशन है.
Right? एक दूसरी टर्म की ट्रांसपोजिशन है, but there is actually something else that I can say. Not just transposition. There's जी Maz?
ये इनर प्रोडक्ट नहीं होगा, मतलब एक ही वेक्टर का अपने साथ इनर प्रोडक्ट ले रहे हैं, तो नॉर्म स्क्वायर कुछ करके है.
Okay. So inner product होगा, लेकिन there's a
I think it will become Z transpose X square norm square.
Okay, so what is Z? Z क्या है? Row vector है, right? Column vector है, right?
क्या है?
And X क्या है?
X is matrix है. नहीं, X भी sorry vector.
It's not a matrix. X is not a matrix. Remember, X is a column vector as well.
जी vector है.
Right? It is a column vector. So Mohsen, I'll come back to you. What will Z transpose times X be? Z transpose is a row vector. X is a column vector of the same dimension, I mean, of equal dimensions, in the sense that appropriate dimensions, so that they can indeed be multiplied together. When they multiply, what do you get?
Scalar.
You get a scalar. Exactly, right? So this is a scalar. What about X transpose times Z?
So same thing.
Same thing as Mohsen, as you said, this is just a transpose of the first thing. But since the first thing is a scalar, the transpose of a scalar is that scalar itself. Right? So this is a scalar as well. And they both are equal. Right? So if I take one row vector multiplied by a column vector and I get some answer, that's exactly the same as अगर मैं पहला वाला transpose कर दूं, दूसरा नीचे कर दूं, so inner product stays the same. Okay, it's commutative. Right? So what this really is, therefore, is equal to expected value of Z transpose times X whole squared. Right? So this thing that we're computing turns out to be the second norm, or the second moment. That's what we defined it as. It's a second moment of a random variable, right? And can this be negative? I mean, can this expectation ever be negative?
No.
No, it cannot be because it's a square there. Right? So this can never be negative, right? And it turns out that this is therefore greater than 0. Right? That's completes the proof. Right? There is a pathological case here though. I mean, I expect that some of you may ask the following question, which is, yes, I know that this can never be less than 0, but perhaps it can be 0 sometimes, depending on what x is. And that's a pathological case which we're not going to. And that pathological case is when all of the x's, or at least one of the x's, is actually not a random variable, but is actually equal to 0. Okay? And that's pathological, we're not going to consider. Right? And we can say that's greater than 0. Josefa?
Sir, I was just confused about how we took the expectation outside everything in the step that you did.
Expectation outside, asal mein expectation to inside. Oh, okay. So that's because of linearity. Zephyr? Right. So we know that again, if this was scalar, right? So if it was scalar, so then a times expected value of x. I know that this is equal to expected value of a times x.
Oh, okay. So we're doing the same thing in vector notation.
Exactly. And within the vector notation as well, it's linear and should be. थोड़ा सा इसके बारे में सोचेगा. And why is it linear? Because this matrix multiplication only involves products with constants and addition. That's it. Okay? And expectations, I know, can go inside, or because they're linear, so they can go inside additions as well, and therefore can come outside as well. Okay? Products can go in or go out.
Okay, sir.
ठीक है. आपको मैं अगर एक बड़ा सिंपल सा एग्जांपल दे दूं, वो ये है कि एक्सपेक्टेड वैल्यू a1 times expect. So just a very, very simple toy example. a1 times expected value of x1 plus a2 times expected value of x2. Right? I can say this is actually equal to expected value of a1, a2 times x1 times x2. Right? Right, Sarva, this is going to give me exactly the same result.
Yes, sir.
So
I understand that.
Value of a times x. So I say a transpose times x, which is equal to a transpose times expected value of x. इस ना कर लें तो तब भी exactly ये result आएगा. ठीक है, this is a toy example for you, and from here I can conclude यार जो मर्जी dimensions हो, this is going to apply. Right, so I'm going to keep on doing this, by the way. So this, Zafa, you raise an important point though. I'm going to keep on doing this for lots and lots of other proofs as well, as they're going to come up. Right, and the underlying principle really is that the expectation is a linear operator. Right, so and it applies to matrices as much as it applies to scalars, that linearity. Okay. All right. So when I say I'm going to keep on applying this, so that's what I mean by that is the following. So we're still at the basics. So linear transformations. So how many of you heard that? आवाज आई किसी को पीछे से कुछ?
Everybody, I think.
Everybody.
Right. So that's my son fighting with my daughter. All right. So maybe one of these days, I'm not sure, एक viral video भी है थी किसी ज़माने में with online teaching. There's a professor who's teaching and then suddenly his son comes up at the back और वो मुख्तलिफ play करता है. देखिए किसी ने?
So you can maybe put it up on the discussion forum.
Okay. So I was actually asking my son to do that for me, but Shaya is not. Ani rapiche. All right. So linear transformation, right? So linear transformation, we have 3 minutes, so I'm just going to introduce a topic and then complete it next time around, which is I have a random vector x, okay, which is of dimension n cross 1. And from that, I obtain another random vector y, which is dimension m cross 1 through a linear transformation. So this is A times x, and this x is n cross 1, right? So where this is m cross n, and this sum addition, and this is m cross 1 as well. Okay. Huzaifa, do you have a question? Yeah, ye pehle kaat kara hai?
Sir, pehle kahi tha, sorry.
All right, no problem. So what we know is that A is and B are constants or deterministic. Okay. So such types of linear transformations are very, very common, खासतौर पे in linear systems. And if there's an input to the linear system, it turns out that you can find out what the output can be related to the input or to the state of a system through such transformations, right? So all you need to do is multiply with a random, with matrix A. Okay? Now, if X is random, you would expect Y to be random as well, right? Okay. But the question then is, if I know the covariance matrix of X, if I know the correlation matrix of X, if I know the mean vector of X, right? What happens to the covariance matrix of Y, or how can the covariance matrix of Y and the correlation matrix of Y or the mean vector of Y be represented as a function of all of these parameters of X? Okay? So that's what we're going to try to do. We don't have enough time, so that's what we're going to do in the next class. But you're more than welcome to try to do this on your own, and we can pick up the discussion next time around. Okay, so I'm going to stop here, leaving you off with this particular expression. Any questions that you have from the content we've covered?